and much more less abstract. Okay, letter graphs. On FPT, I'll go for them. So I'm gonna first define what is a K-letter graph and maybe give some examples and sketch the proof, which is based on a small observation, and then define monadic second order logic. So graph G. So G is a K-letter for K fixed. So I'm assuming that K is a fixed integer. So K-letter graph. So if there exists a directed graph D, so this is a directed graph. So on K, on elements on K vertices, and a linear mapping. So linear ordering. So by a linear ordering of V to G, and partition of V to G into K sets, so, and such that, so X, the vertex of G, if and only if pi of X is smaller pi of Y, and X, so the partition and ij in D with so two K sets, so V1 Vk with X in Vi, J in Vj, Y, sorry, yes. Or X, Y in the same part, in the same set, and Ij. So here I assume that Y is different and Ii in K. Okay, here I assume that J is different from I. This is important for the rest. So that's why, so I different from J. Because in the characterization we will make difference between both. That's why I prefer to make a difference. Otherwise, this is included in this one if I assume I did not different from J. Yes. Pi is on a linear ordering, so pi of X, pi of Y.
But then they're equal.
Ij. It's not a linear, so I have a partition and then a linear ordering. Then from this linear ordering now, so I'm asking what are the edges. So if I have X, this is X, so this is Y. So when can I have an edge from X and Y? So I'm only looking at the sets containing X and Y. So the sets containing X Vi, the sets containing Y Vj, and I'm asking whether Ij is in my solution, is in my D or not.
So pi is in ordering of the V1?
No, it's an ordering of V. Whole graph. It's an ordering of whole graph. And then if you give me two vertices, X and Y, then I'm looking whether I can put an edge. And whether I can put an edge, I'm just looking whether the pair Ij is in D.
Linear ordering tells you what order to look at the set.
Yes.
Exactly.
Exactly. So the linear ordering tells you how you can. So you can say, look at it in another way to see it. So it's like, okay, you have a word of size n on K alphabet, on an alphabet of size K. Now, what you will do is just you pick two positions and you ask whether the vertices corresponding to these positions you put an edge or not. Then you only look at the graph D. if the letters on these two positions are adjacent in the directed graph key, then you put an edge. Otherwise, you don't put an edge. So now, is it fine? Okay. Yes, okay. Equivalent. So equivalent definition. So is I have an alphabet on K. So K vertices on K element on size K. Okay, that I will say 1 to K. Now then I pick a word of size n on sigma, and now the associated graph G, so what I call GW, so as n vertices, one to n, and now I will put an edge ij, right, has an edge. So I put an edge between ij if, so word w, so if wi, wj, okay, this is maybe not the, so a1 to ak, so if wi, wj is in D for a fixed D.
We can understand that D is every of D is extended to
Yes, yes. And
connected completely.
exactly. And then after you look at the ordering, you look at the ordering on connecting them. So it may be symmetric in the sense that, okay, if you have GA in JI in your set, then you don't look at the ordering, because no matter the ordering you will find JI. So one not difficult fact about this K letter graphs. So if a graph has one, maybe clique-width was not defined.
What does have to do with X?
Yes, I will tell it. So okay, so since you define it, then okay. So now you have this fact. I call it a fact by Lozin and the stuff. So if neighborhood diversity is K, then it is a K letter. And it is a K letter graph. Now another fact 1, so another fact 2 is that if J is a K letter graph, then linear rank width is at most K. Linear clique width at most K plus 1. So not difficult to do. Everybody know what is linear rank width, what is linear clique width? That's, and so that's more or less what we will use. So another observation that is not that difficult is so fact 3 is that G of W is an induced subgraph of G W prime if only if W the subword of W prime, and then this implies that subsequence, okay, I don't, the name if you prefer subsequence, so some So a consequence of this is that k-letter graphs are well quasi-ordered by induced subgraph. You use Hickman's lemma and it's fine. So this means that k-letter graphs are WQ by induced subgraph. And then, so one question is, can we bound the size of the abstractions by Hickman's lemma? So then the question is, can we compute the abstractions or the excluded, and also can we recognize in polynomial in FPT? To also FPT means the parameter as being always k, the parameter always being k. Okay, so that it is finite, but can you compute them? This is yes, but here you will get so you have a bound, but you don't know how to compute the abstractions. So, and for each of the abstraction you are looking, and this is n to the size of the abstraction. Is it the bound depend? Probably so. The bound should depend on k, but the theorem doesn't tell us that the bound depends on k. The Hickman's theorem.
So these are abstractions by induced subgraph.
Yes.
But you can code it as an MSOL formula.
That's exactly what I will show, and then you can automatically encode it by MSO formula, and then this gives this FPT. So, and so because it has boundaries, then so what I want to say is, how can we give a bound? Because you know that you have under this, but what I mean is a constructive one. FPT constructive one, because this theorem doesn't tell you how to compute the abstractions. Is it okay? I don't know any explicit construction from the Hickman's lemma. Maybe there is, but I don't know any. Okay, so why does it? So these k-letter graphs appear in enumerative combinatorics with a subclass. Okay, a subclass of k-letter graphs. So is of interest in enumerative combinatorics. So what they call the K-readable permutation. So K-readable permutations. So what is a K-readable permutations is you have a matrix, a KK matrix. On 1 minus 1 0, and now so this you can construct some lines and on a grid. So pick the grid on k times k, pick a k times k grid. So now what you will do is to construct lines on each cell. So the lines is up, So the lines is going up if the value is 1. So you go up if the value is 1, and you go down if the value is -1. You go down if -1, and you don't care about 0. And then for a permutation is K-readable if you can write down the permutation following these lines. So going up and down. So yes, that's what I will. So for instance, you can maybe the 2-2 grid, and then if you have this, so meaning this is 1, so -1, 1, and -1, so -1, so this is -1, 1, -1, and 1. So now, for instance, has a K-readable permutation. For instance, I can have 6. Okay, maybe it's not the right. So I can have, for instance, 3. That I can draw 1. Then it's just after. So they cannot share columns and rows. Okay, so they cannot share columns and rows in the usual meaning of representation of a permutation. So 1, then I can have 1, then I can have here 4, then I can have, for instance, 3. Oh no, just 3, so 5 here, then 4 and 2. Here I put 2. Okay, so this is a 2-readable permutation because I can have 3, 1, 5, 4, 2. I follow the lines always. So I'm either going down or going up. So this is a 2-readable permutation.
Within like you have this diagonals based on is 1 or -1.
Yes.
And then you pick points inside.
Exactly. I put points inside the lines, and by respecting the fact that if I'm going from I to J, if they are on going up lines, then I should be smaller than J, and if I'm going down in a line, then J should be greater than J. It should be smaller than I. So 4, 5, 4. So I'm going down, and the 4, 1.
What is the permutation?
This is 3, 1, 5, 4, and 2.
With this is reverse the sign on 3 of the blocks, only the one that I hold.
I don't say that it's unique.
Oh, so between different blocks you don't care.
Yeah. I care only the fact that it's going. So what Lozin and blah 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 showed is that another lemma is that if G is K-readable, or okay, if a permutation is K-readable, then it is f of k letter, then the permutation associated graph is permutation associated graph is f of k letter graph. It's even k square. It's
Before you go on, can you explain in more detail what exactly is this case by K representation?
You pick a KK matrix on 1 minus 1 0.
That one.
Yes. Then now you take the KK grid, and then you put if you form KL, if they are adjacent, then you put an up down an arrow going up if it is 1, and you also or you put an arrow going down if it is minus 1. So this is so 1 minus 1, so minus 1 1.
If you have many points in the block, they have to be arithmetically.
Yes. They should follow the line in the permutation.
They have to be really arithmetically.
Yes, inside.
Increasing, not just monotonically increasing.
No, they should be monotonically increasing or decreasing.
Arithmetically increasing.
No.
So they don't actually have to be linear, co-linear. You require the points, like let's say you had 3 points in the top left or 4 points in the top left block. Would they have to be 4 co-linear points?
No.
No.
Yes. They should be in the same line. You should.
Not just monotonically.
No. They should be in the line. They should be on the line. Yes, it should be on the line.
So far.
It doesn't.
It's not a matter of embedding the drawing. Actually, that's just representation. Dividing k-square segment, and each segment is non-trivial.
Exactly. Easy enough.
So you don't require co-linearity. So what about if you had like 3, and then let's say you had 4, and then 3, 4, 10. Let's say the first 3 numbers were 3, 4, and 10.
I'm just reading the permutation from left to right.
Yeah.
So
let's say the first 3, 4, 10.
3, 4, 10, right?
So it's increasing, but they're not collinear, right? Because between 3 and 4 you have slope 1, and between 4 and 10 you have slope
Yes.
6, right?
Yes.
So they're not on a line, but they are increasing. Is that acceptable in the first block?
I can have in a block. Yes, is this acceptable in a block?
Even though they're not collinear.
Yes. I have just to draw them anywhere on the line. So. Or decreasing segment. This is just what I'm considering. It's either increasing on a segment, decreasing on a segment.
So is it like you choose points? So I choose points in the diagonal with a different x coordinates, and then just read from the right, or
They should be also different y coordinates.
different x.
X and y coordinates. Yes. They should not share neither a row nor a column.
And then read from left and right.
Exactly.
Ranking.
Yes.
On the y coordinate and the static permutation, or
No. Yes. You then you just follow the axis coordinate to read them.
You make sure that you pick like k-square permutations. And inside these permutations, it's
Which k-square permutation? It's just the matrix you mean?
Yes. So you partition it into k-square thing.
Yes, the grid.
And inside this k-square, you have to be either increasing or decreasing.
Yes.
depending
On the sign. Yes.
I see. Or
Yes. Or then I don't do anything if there is 0.
0 is I don't care.
Yeah.
So it can't be the same.
Yes. That means just I won't draw anything inside.
you want to draw anything.
If it is 0, this is just they will share the row, or you can only draw 1 because otherwise then you share the same. It can be on. Then you can just pick some small. You can put it on the right side or on the left side, so you don't care in this case. Well, I wasn't.
It's not like you don't care. It's not like you don't care. It has to be 0, so you can only draw 1 or.
Yeah, but this one you can move it on the left or on the right side because.
And you have to read. Could you the 1 in your example? 3 is correct in the 1, 5 is correct in the 4, and those 2
No.
lines.
These are not in the same permutation. Only 5 and 4 are in the same subgroup.
Yes.
How do you find
So
number 1
that's
in the
the only thing that
Number 1 is here.
the one we don't care about.
This is 1, so I go 3, 1,
Okay.
3 move.
5, 4, and 2.
And you only care about 5 and 4.
Yes.
Well, 4 is
try to resolve 3, right, on the y coordinate. Is it okay?
But I'm looking at the left I'm reading from left to right.
Yeah.
So the y coordinate when I'm reading is not important because I'm reading from left to right. I'm reading from left to right, so the y coordinate doesn't matter when you read. But when you draw them, they should not share the same y coordinate, and so no x coordinate.
So for instance, the same picture, can I put that, like instead of 3, I put 4 and then...
Here?
Yeah, and then replace that 3.
Yes.
Okay?
Yes, because you are going down 4, 1, 1, 5, 3, and 2. You are still following the rules. You are still following the fact that you are going up or down at each step.
So just look at the number coming next.
Yes. Yes.
So you do care in the first rule that you're going down?
Yes, because it's -1, so you should go down.
Just look at consecutive pairs.
2 consecutive pairs, you should care about that you are going up or down. That's what I said before.
So it's not what I understood.
5 you're going up, and 1 says you should be going down, and 5 says you should.
Yeah, but the next is 1. So then 1 is smaller than 5. So then you are going up.
They never overlap in different yeah, in different blocks you don't care, right?
Yeah.
So you could have 10 instead of 1, and that is equal. So
Yes.
as long as if you have only one entry in a block, you don't care if it's plus, minus, or 0.
Is this also 10?
Is that correct? That
No,
is
no.
the one with the 10 is 0.
Yes, no.
Why?
4, 10, no. 4 is going now. Yes. Yes, yes. You have to go up. You have to go up in a permutation.
Okay, so if you read your permutation from bottom to top, you have to go in order 1, 2, 3, 4, 5.
The definition is quite. Yes.
This diagonal.
Sorry. Here I can. Yes, I can still put 10.
So,
To where? Here. But then I should put. I cannot because here I will have 3. Like if you do care when you are in the same and next and when they share.
For me, the least question actually makes sense. So the lowest number, if you look at the y coordinate, is this always number 1?
No.
Of course not.
so I think what you want to say is that you just sort them by the x coordinate, okay?
And then
And then like look at the sum point. Now if it's on the up diagonal, then the next number should decrease.
exactly.
If it's on the down diagonal,
Then it should.
the next number should increase, and that's the only condition.
That's yes. Yes.
Okay. Now we got the script definition.
So what Mathilde and others proved on this is that, for instance, they prove that it's WQ, but then you have it for free. It's also algebraic, so it's rational. So then you need an encoding different from this, and also then you wanted to have the number of abstractions and compute them. So they cannot, but in their paper, so they give a characterization that is monadic second order definable. And then now, by combining this and what I was supposed to talk about, this, then I can still answer that question, the fact that you can still compute their abstractions. So I'm just gonna give a short lemma saying why it's MSO-definable, the class of K-letter graphs. And it's just an encoding, and then it's not that difficult to find it. So yes, I think we will. I was not intended to.
Like 10 minutes.
Yeah, so
It's okay.
we all fine, right?
Yes, yes,
That's
yes.
nobody's starving, right?
So now I'm fixing. So I'm fixing a partition into K sets. So V1 VK and K square, and then I am asking whether I can find an ordering of my graph G satisfying the fact that I have this partition from the K literacy of the graph, and this encoding D will give me the adjacency. So now the compatible graph of this is the following. So now G is given, right? Okay, so G is given. So if I have vertices V of G, and the arcs so are the following: x, y, such that x, y is an edge, ij is in D, and x is in Vi, y is in Vj, I different from j. So, or xy such that, so either I have this condition. So if I have xy being an edge, and I have ij being an arc of the encoding D, then in my compatible graph I add an arc from x to y if x is in Vi and y in Vj. So what does it mean? This means that if I want a linear ordering, because if you remember, I have to put an edge if x is before y and there is the letter associated to x and the letter associated to y are adjacent in the directed graph. So this means that x should be before y, right? Now, if there is no edge between x and y, so what does it mean? That means y should be before x. Then I add the arc yx, and so that xy is not an edge. Okay, ij is in D, and the fact that x is in Vj and y is in Vi. X in Vj, y in Vj. So this is a compatible graph we will construct. If you give me a partition and you give me a directed graph, so what you construct is this directed graph, and then the observation you may have is that G is a k-letter graph with partition V1 Vk and encoding D if you only if this is a DAG. So G is a k-letter graph with partition V1 Vk and encoding D if and only if compatible graph is a DAG. Okay, if only the compatible graph is a DAG, then you can now if it is a DAG, what does it mean? That means you can do a topological ordering and find the order, and it will preserve the precedence. Now then if you know logic, this is encodable in monadic second order logic, because the edges as you see, if I fix the partition and I fixed D is K, something on K, then on G I can describe the compatible graph. Since on G I can describe the compatible graph, so I have an transduction from this encoding to my K letter graph to the word describing it, and then any formula, then I can encode this in my original graph G. And what does it mean now? Fixing the partition is guessing the partition. So guessing the partition, this is monadic second order logic, and I have to do it all for all subgraphs. Then this means that from this observation I have a quick FPT algorithm and an effective one. Now what I'm going to use is the fact this again, this formula, okay? So a corollary of this there is an MSO formula phi k defining graphs, defining K letter graphs. So you have such a formula defining K letter graphs. So this means FPT algorithm, effective algorithm. So now for the abstractions, sorry, it will depend on D, but this is f of k square, 2k square, all the subgraphs of size D. So I will, in some sense, for each of them, so it will always be a partition and a D. So I want the formula will be something like that. So for any D, then what I'm doing is guessing a partition, constructing, so I guess the partition, and check whether the compatible graph is acyclic. So this is an MSO formula. The description of the edges, I can define them in MSO formula on the graph. Then this checking also is MSO, and then I use Cursel and Sangil to check to check that it is definable. So now the next, for the abstractions, what you can observe, so what you can observe for the abstractions, the following. So if G is an abstraction for K letter graph classes, for K letter graphs, so then G is a 2K plus 1 letter graphs. So then I have again a formula describing the abstractions, because what I will do is, it is an abstraction, meaning for any vertex I will remove, I have a K letter graph. Then this is for all V, I satisfy this formula, and since it is a 2K plus 1 letter graph, then I can check that G is a 2K letter graph, and then I can check whether it is an obstruction. So now obstruction, so this means there is an MSO formula describing obstructions. So now from this MSO formula describing obstructions, I can bound the size. So let me take the minimal automata. So that I call obsk for obsk, and with S of k states. So now what I do is assume that my minimal obstruction has this size, has a bound bigger than, has size bigger than S of k. It's a 2k plus 1 letter graph. That means it has bounded linear clique-width, and then I can check this formula on the graph. So assume now assume G is an obstruction, and S of k. So let's take the associated linear clique-widths expression and run the automata. Right? If you run the automata, what you will realize that you will have at least two parts with the same state. So if you run the automata, because the number of vertices is bigger than S of k, so the linear clique-width expression is just a linear ordering of the graph. Then if I run the automata, then because so this means I have two nodes with same states. Okay, in the clique-width operation, so that means, so I have I have j, so this is I plus 1, so this is j plus 1, and blah blah blah. So what I have now is that if I'm looking at the next state from here, and at the next state from here, to answer, it depends only on the state I given here and on the value of this vertex. Okay, and similarly, so if I replace now this graph, if I replace this graph by this graph, which is an induced subgraph of my graph, I am still satisfying the formula. If G was satisfying the formula, then if I replace Gj by this subgraph, induced subgraph Gi, I am satisfying still the formula, and meaning that I have an induced subgraph which is an obstruction, which is not possible. Then the size is bounded by S of k.
So this is a proof without using well-quasi-ordered.
Yes, that the size is bounded. So I don't use any well-quasi-ordering. That's why I call it effective algorithm. Well, effective in the sense that I can run over all subgraph of size at most S of k. And so this, then if I combine this with definition of K-readable, then I can still get that this number of abstractions for K-readable, I can construct them. And because it's a bijection which gives you a monadic second order form. It's a bijection to regular languages. So the, how to say, the rationality of K-readable graphs is a bijection to regular languages on words, and regular languages on words are MSO-definable. And these are regular words, more or less. And then any K-readable permutation, I also have a finite obstruction I can compute, I mean. And so probably this can be reduced. So a question is S of k equal to poly k square, poly k, to get a better bound. I can construct the automata from the formula, but the size is horrible. And so this is a nice observation that using automata theory, easily you can compute abstraction for a subclass of bounded clique-widths. Yes, thank you.